Hey, so hi there folks. So in this video, another video for number theory, still in module 2, divisibility theory and the fundamental theorem of arithmetic. We're going to talk about the divisibility relation. So the divisibility relation says that suppose we let r to be 0 in the division algorithm. Again, r is the remainder. So we have the division algorithm as this: a, the dividend, equals b, the divisor, times the quotient plus the remainder, which we say that we will let it as 0. So therefore a is equal to bq. Then we say that b divides a, or b is a factor of a. So first, we say that in words that b divides a, or b is a factor of a, or a is divisible by b, or a is a multiple of b, and then we write this as in this notation. Okay, so it has a lot of pretty names. So again, we can read this as b divides a, or b is a factor of a, or a is divisible by b, or a is a multiple of b. But I want to make it, to call it the fastest way, b divides a. That can be it. Okay, so we write this as b divides a. Just take note, it's very important to write this not in this manner, because we can read this as b divided by a. So it should be that the line is pretty much a vertical, straight vertical line, not a diagonal. So this, we write it this way. So let me box that. So if b is not a factor of a, if it's not a factor of a, so therefore we write it this way. So we put the vertical line and then we put a cross behind it. So we put a cross sign here. So therefore b does not divide a, or b is not a factor of a. Okay. So how do we have this? For instance, we have 3 divides 12. Why is it so? Because we know that 12 divided by 3 is 4. So therefore, 3 divides 12, because we can write this as 12 is equal to 3 times something. Okay, so specifically, that's 3 times 4. Okay, so therefore, indeed, 3 is a factor of 12. Likewise, 5 divides 30, because we know that 30 is equal to 5 times something. Specifically, it's 5 times 6. So therefore, indeed, 5 is a factor of 30, or 5 divides 30. But here we can see that 15, or rather 6, does not divide 15. Again, 6 does not divide 15, or 6 is not a factor of 15, because we know 15 as, if ever we're going to use 6, really, okay? If we're going to put 6 here, 6 would be times 2 plus a remainder of 3. Okay, so 15 is equal to 6 times 2 plus a remainder of 3. So wherein this remainder must be strictly 0. So therefore, we say that 6 does not divide 15. Okay, so that's for the divisibility relation. And also we will be using this notation pretty much a lot after this video. And just right before this video, you should watch the Pigeonhole Principle, because our next example will be using that one. So example, let for one example, for the division relation. So let b be part of the integers wherein this is strictly greater than or equal to 2. Okay, so that b be an integer greater than or equal to 2. So suppose b plus 1, there are b plus 1 integers which are randomly selected. Prove that the difference of two of them is divisible by b. Again, so b plus 1 integers are randomly selected. Prove that the difference of two of them, is divisible by b. So we're going to give a proof from this example. So let's have this. Okay, so first up, we will let q be the quotient, q be the quotient, and r the remainder. Okay, when an integer a is divided by b, when a is divided by b. Okay, then by the division algorithm, by the division algorithm, we have A equals our usual thing, BQ plus R, where R is between B and 0, can be equal to 0. Okay, so the B plus 1 integers yield B plus 1 remainders. So the B plus 1 integers yield B plus 1 remainders. So these remainders, we will consider them as in our pigeonhole principle, these are the pigeons. But there are only B possible remainders, which we will consider as the pigeonholes. So if we have, again, let me read this again. Let Q be the quotient and R the remainder when an integer A is divided by B, then the division algorithm A equals BQ plus R, where we have R between B and 0, but R can be equal to 0. So there. Then we have B plus 1 integers yield B plus 1 remainders. We will call this our pigeons. But there are only B possible remainders. Okay, there are only B possible remainders, which we will call our pigeonholes. Therefore, we can see by the pigeonhole principle that two remainders must be equal so that it can fit to the B possible remainders. So let us write that in informal way. Therefore, by the pigeonhole principle, two of the remainders must be equal. So we will let x and y be the corresponding remainders or corresponding integers. Okay, so we will let, after this, we'll show now that these two numbers, okay, these two of them, okay, are divisible by b. So let x and y be the corresponding integers. Then we have x equals bq sub 1 plus r, and y equals bq sub 2 plus r for some quotients q sub 1 and q sub 2. Therefore, we can write this as x minus y is equal to, so we know x, the value of x is bq sub 1 plus r minus the value of y of bq sub 2 plus r. So what we have is which is further equal to, um, we can cancel the r's. So if you want to have the detailed step-by-step solution, distributing the negative signs, we have minus bq sub 2. What we will do then is isolate the b by the common monomial factoring. Okay, so from here, we can see that x minus y is equal to b times the quantity of q sub 1 minus q sub 2. So to write that, that is x minus y. Okay, so that is x minus y equals this one. X minus y is equal to b times the quantity of q sub 1 minus q sub 2. So clearly we can see here that x minus y is divisible by b. Okay, so x minus y is divisible by b. This is the end of proof. That, in other words, b is a factor of x minus y, which we have proven, and this is the one which is asked of us from the first part. Okay, prove that the difference of the two of them is divisible by b. So we have a difference of x and y. It is divisible by b. Okay, since we know that for the division algorithm, divisibility means that we can that other one b is a factor of a. Okay, so we can see here that b is a factor of x minus y. So x minus y is divisible by b. So yeah, that's the end of proof. That's it for this video for the divisibility relation. The highlights of this video shows us the notation for divisibility relation and also one application of the pigeonhole principle in action. Okay, that is using also the division algorithm and such. So thank you very much for watching. I hope that you would like and subscribe this video, and um, hoping to see you in the upcoming videos. Okay, so thank you and see you soon.